class, this is Professor Hiley. I want to give a follow-up example to the existence and uniqueness discussion I did in the last video. And I want to give you an example to make the theorem real for you, to help you see what it's saying in an example. Alright, so the example I have for us right now is an x squared y prime double prime minus 2xy prime plus 2y equals 6. And I'm going to propose that we use the interval 0 to infinity for this solution. And I'll explain why we're selecting that interval as we go. And my initial condition is that y1 equals 2 and y prime of 1 is negative 1. So I just wanted to point out real quick that this is a linear first order differential, linear second order differential equation. We can see the second order in the y double prime. Why is it linear? It's linear precisely because any coefficient is either in terms of the independent variable x or a constant. If we had a y, or if we had this raised to some power or did something funky like that, then it wouldn't be linear. But this is linear, classic linear, higher order differential equation. Notice it's second order. How many conditions do I have? I have 2. If we would have a third order, we would have 3. And so this goes up to y double prime. Notice that my initial conditions stop at y prime. You stop one level before the highest derivative. So if you had a third order equation, you would have a y double prime initial condition. Okay? But we only have second order, so we stop at y prime. So this fits the bill. It also fits the bill that on this interval 0 to infinity, that all of these coefficients, this, and this, are all continuous, right? So this is that a(n) of x, right? And this was our a0 of x. In this case, n is 2, right? And this is a1 of x, right? I'm just showing the same, talking about the same notation that I did in the last video when I mentioned the theorem. So the height, all of these, and this would be like the g of x that I said in the statement of the theorem. So these are all continuous on this interval. None of these are 0. In fact, the leading coefficient is not allowed to be 0. So, and on this interval, it's not. So we meet the criteria. So the theorem says there's a unique solution then to this equation. And that solution happens to be this solution right here, negative x plus 3. And in ensuing videos, I'll show you how we put a solution together like this. It's not really as mysterious as it seems. A lot of times what we'll do is we'll start to guess at a solution. So for example, when I look at this equation right here, I know that 2, for example, 2 times 3 is 6, and the derivatives of 3 are all 0. So just the number 3 by itself, y equals 3, is a solution to this equation. The 3 is part of this solution. But so this solution here is a unique solution. On this interval with these initial conditions. Okay? If we change the initial conditions, it would change our equation. Okay? As long as we're meeting the criteria. But this particular equation meets this, satisfies this equation, meets these initial conditions. And let's check, in fact, that I'm not just making this up, that this is actually a solution to this. And this is something you should do and be in the habit of doing, especially now that we have higher order equations. You should be able to plug in and check solutions. Because when you go through a complicated process, it's easy to make a mistake, and you want to be able to know that your solution is correct. So let's check out the solution and see if it does meet the criteria. Okay, so if y is this, then y double prime is -1, and y prime is -1, and y double prime is 0. And so then I want to plug these into this equation, make sure it works. So I take x squared times 0 minus 2x times -1 plus 2 times -x plus 3, and I'm hoping that's 6. So I'll put a little question mark there because I'm not sure, but I'm hoping it's the case. Okay, so then of course this is 0. This is plus 2x because a negative times a negative is a positive. This is -2x, and then 2 times 3 is 6. And lo and behold, these cancel out, right? 0 plus 6, we get 6 is 6. So this does satisfy it. And by the way, it does meet the initial conditions. Because if I look at y of 1, that's -1 plus 3, and that is 2. And y prime, regardless of what you plug in, is y prime of 1 is -1, because it doesn't matter what x is. So the point is that this is a solution that satisfies this equation, and it meets this initial conditions. And by the theorem, this is a unique solution. There is no other solution besides this. Okay? I mentioned that 3 by itself would satisfy this equation, right? But y equals 3 does not have these initial conditions. So the idea of this being a unique solution is not just that it's satisfying this equation, but that it's meeting these 2 initial conditions. So let me show you what happens though when we expand this example out and change it slightly, and let me show you something else. Okay, so I'm going to keep the same equation. I'm going to change the initial conditions though, and I'm going to change the interval. Okay, so I'm going to look at, we'll say y of 0 is 3, and we'll look at y prime of 0 being 1. Okay. And I'm going to think about this. We're going to expand out our interval and look at what is a solution. Is there a solution to this equation with these conditions, and is that solution unique? Okay. Well, again, I'm going to seemingly grab a solution out of the air, but again, we'll look at how we get these sort of solutions as we go. But I claim that my solution to this is y equals cx squared plus x plus 3. Okay? I claim that this is a solution to this equation. Okay. First of all, let's check and make sure it meets the initial conditions. Well, obviously, if you plug in 0, we see that y of 0 is 3. Y prime would be 2xc plus 1. And again, if you plug in 0, you get this condition here. So this equation doesn't meet these 2 conditions. Let's finish, let's take the second derivative, and let's see if it actually makes this equation work. So this then becomes, y double prime just becomes 2c. Okay, so now what I want to do is just plug these elements into this equation and see if we get 6. So I have x squared times 2c minus 2x times 2xc plus 1. And then I have plus 2 times this, cx squared plus x plus 3. And we would like to know, is this 6 or not? Well, let's check the math here. So this equals 2x squared c, or I'll put the c first, 2cx squared, and then this is minus 4cx squared minus 2x plus 2cx squared plus 2x plus 6. And again, I'm wondering, is this 6? So I'll put question marks here because I don't know, okay, until I simplify this. Well, let's look at the x squareds. So I have 2 plus 2 is 4, 4 minus 4. These all cancel out. Negative 2x and x can't 2x cancel out. Lo and behold, I get 6 equals 6. So my point being is that my proposed solution is a valid solution. Now here's the thing I want to point out about this one. Notice that I have a c here, right? That means I didn't say what number that was. So this could have been 3x squared plus x plus 3. Or it could have been negative 5x squared plus x plus 3. The solution, this meeting the criteria of both these conditions and satisfying this equation were irrespective of what c is. So in this case, there is a solution to this system. Here it is, but it's not a unique solution. So the theorem guarantees that there's supposed to be a solution and it's supposed to be unique. So what went wrong? Why did we run into this? Well, we ran into this precisely because we picked an interval that contains 0. What's the problem with 0? Well, these functions are all certainly continuous on this interval. That's not the problem. But what the problem is that the lead coefficient is not allowed to be 0 on the interval that you're using to get a unique solution. So because we picked an initial value that made this leading coefficient 0, it allowed us to not be able to have that unique solution. Okay, so that's an example of. And also, let me point something out here too. If I had tried to change these initial conditions from what they were, let's say I tried to say that this is 2, right? Well, here's the problem then that you'll find out is then we could run that there's no solution. So if you violate this being 0 in your interval, or if for some reason these are not continuous in that at your value that you're in an interval and a value around that, then you run the risk of having either an infinite number of solutions or no solution. And so in the next video, we'll start to look at how a solution like this, we'll look at some principles that will allow us to be able to put solutions together